Okay. In this video, we're going to talk about the concepts of oxidation and reduction, especially with regards to organic chemistry and carbon-based molecules. But before we talk about oxidation, reduction, and organic, let's remind ourselves about these concepts as the way you learn them in introductory chemistry. And oftentimes you looked at oxidation reduction with redox reactions and electrochemical cells. So if we look at this reaction here, it's a pretty straightforward redox reaction. Copper 2 plus is becoming neutral copper. Neutral zinc is becoming zinc 2 plus. Now pause the video here if you need to and try to identify whether copper 2 plus is being oxidized or reduced and whether neutral zinc is being oxidized or reduced in this reaction. Hopefully you are able to identify that copper 2 plus must be gaining electrons in order to become neutral. A gaining electrons is a reduction. So copper 2 plus is being reduced to copper neutral. Zinc is being oxidized to zinc 2 plus. The way I remember these is with that mnemonic, right? The loss of electrons is oxidation, and the gain of electrons is a reduction. Leo goes Gur. Copper is gaining electrons, it's being reduced. Zinc is losing electrons, it's being oxidized. Now that we've got that concept down, let's think about it with regards to organic chemistry. In organic, we're focusing on the carbon chain, okay, and whether the carbon backbone of a molecule is gaining electron density or losing electron density. So let's think of a simple reaction here where our pentane molecule has turned into an alcohol. Okay. Now, do you think this is an oxidation reaction or a reduction reaction? In order to answer that, sort of theoretically, we need to think about whether the electron density of the carbon chain is being increased or decreased as it becomes an alcohol. Now, we know that oxygen is more electronegative than carbon, and so by generating this alcohol group, we've generated a polar bond where the oxygen has a partial positive charge and the alpha carbon here has a the oxygen has a partial negative charge and the alpha carbon has a partial positive charge. Now, if you can just identify that, you can see what has happened to this carbon chain. It's become more positive. So, has it lost electron density or gained electron density? If it's become more positive, then it must have lost electron density, and therefore this is an oxidation reaction. This makes sense, right? In order for an alkane to turn into an alcohol, we have to add oxygen to it, and so it must be oxidized, right? Oxygen is a great oxidizing agent, and it oxidizes that alkane to an alcohol here. So really, when we think about focusing on this carbon chain and asking whether the carbon chain has lost electron density or gained electron density, really we can count how many carbon-oxygen bonds are present in a molecule to determine how oxidized it is. And when we think about the different functional groups that are present in organic chemistry, we can sort of rank them from, least oxidized to most oxidized, and the way we've ranked these is primarily based on how many carbon-oxygen bonds are present. The more carbon-oxygen bonds that are present, the more electron density is being removed from the carbon chain by the oxygen, and the more oxidized that carbon chain is. Right? So here's alcohol. We have one carbon-oxygen bond. Aldehyde has two carbon-oxygen bonds. Ketone is got two carbon-oxygen bonds also, but it's generally more oxidized than an aldehyde, right? If we think of this hydrogen here, it's not going to be pulling electron density. If anything, it's going to be pushing more electron density onto the carbon, and so this sort of counteracts some of the carbon-oxygen bonds. That carbon-hydrogen bond is lacking in the ketone, and so it's more oxidized. Carboxylic acids have 3 carbon-oxygen bonds, and then carbon dioxide has 4, the most oxidized, right? The carbon in carbon dioxide has lost a lot of electron density, being yanked away through inductive effects by the oxygens here. Therefore, it has lost electrons. It's very oxidized. And we can visualize that with a couple molecules here. Here's simple pentane, a boring alkane, non-functional. And if we sort of map out an electrostatic potential map, looking at the electron density in this molecule, we can see it's pretty evenly distributed, the electron density, right? This is a good illustration of why alkanes are not that reactive, right? Except in maybe combustion reactions or with radical reactions. There's really no differences in electron density in the molecule. It doesn't have any obvious nucleophiles or electrophiles, and is pretty non-reactive. Now let's take this pentane and oxidize it to pentanol. We've got our alcohol group here. We've generated a polar covalent bond where the electron density it should be higher on that oxygen. And so if we map out the electrostatic potential map, we can see that we do have higher electron density on the oxygen, as indicated by the blue color. And the carbon chain has lost some electron density because of this light blue here. This also could make this a more reactive molecule. We've got electrophiles and nucleophiles present in here. So this is more oxidized than regular pentane because of this polar covalent bond that's removing electron density from the carbon chain and distributing it more on the oxygen of the alcohol.